Hi everyone, my name is Sarah and I live on the sunny side of Washington State. Here we have random tumbleweeds, gorgeous mountains, and a beautiful Columbia River which produces a tremendous amount of hydroelectric power for the U.S. All around us you can see bluffs, wildlife, and natural vegetation. Throughout history, this area contained American Indian villages and was utilized for fishing and hunting. It's also been used for trapping, mining, ranching, and most recently, irrigation and farming. Flashback to 1942. At this point, the United States was wrapped up in World War II. The Pacific Fleet was attacked at Pearl Harbor on December 7, 1941. The day after, President Franklin Delano Roosevelt gave an impassioned speech to Congress to declare war on Japan. Shortly thereafter, Germany declared war on the United States. Remember Einstein's letters to FDR about uranium fission and Germany's potential capabilities? Well, by 1942, the U.S. government decided to move forward with a full-scale investment in the bomb program. Here to tell us more is Robert Franklin. Thank you so much for being here.
Well, thank you for having me.
Why is it called the Manhattan Project if we're nowhere near Manhattan?
Well, that's a really good question. So this was a top secret, very, very top secret project. Even the name of the project, they didn't want that to give anything away. So they decided to name the project out of the office which ran it, which was in Manhattan.
General Leslie Groves was appointed to lead this top-secret project. Groves, known for leading the construction of the Pentagon, now became responsible for managing a project that would coordinate the activities of these Manhattan project sites for one purpose: to build an atomic weapon. The challenges were immense, including how to keep it a secret, how to build all the necessary infrastructure, and how to keep American communities safe. It was a massive project that employed 130,000 workers and cost $2.2 billion, which is almost $40 billion today. Wait, so what exactly is this reactor behind us?
So this is the B Reactor, the world's first full-scale nuclear reactor, and this would take uranium and transform it into plutonium, which was used in the atomic bombs.
Why was Hanford chosen as a site?
Well, a couple reasons. There was the X-10 reactor in Oak Ridge, which was kind of like a pilot, like a baby of the B reactor behind us. But they didn't really want to put all their eggs in one basket because Oak Ridge was also enriching uranium. So they needed a location that was far away. They wanted somewhere out west. So Lieutenant Colonel Franklin Matthias was assigned with finding a new location. And Hanford here had everything that they needed. It was pretty rural. Only about 1,500 people lived in the 600 or so square miles that was taken for the Hanford site. It was pretty remote. In 1943, this wasn't a heavily populated area of Washington State. It had, like you mentioned, the beautiful Columbia River nearby, which flows year-round with cool, pretty clean water that was used to cool the temperature of the reactor. So it was really a perfect confluence of factors.
You mentioned that people were around here in towns. Like, what happened to those people?
Well, that's a good question. So there were about 1,500 people in this area here that now comprises the Hanford site. And beginning in 1943, they got letters in the mail informing them that because of the War Powers Act, the U.S. government was going to be taking their land. And also to these people, many of them thought this was home and they wanted to help the government in times of war, but it's hard to give up your home and to not know why. This was a top secret project. To learn more about it, why don't we go check out the old Hanford town site?
Cool, let's go. Whoa, what is this place? It looks haunted.
Yeah, it's a little eerie, isn't it? This is the old Hanford High School, from, of course, town named after the town of Hanford, and it's been abandoned now for over 75 years. So, like I said, all the residents here, the farmers and townspeople had to leave, and in their place was the Hanford construction camp, kind of where we are. We're in the northeast corner of that now. This area, 1,500 people, transformed into a city of 45,000 people, the fourth largest city in the state of Washington from 1943 through the early part of 1945. They came from all over. They came mostly from the South. DuPont and the Army Corps recruited black and white workers to come here. Black workers at Hanford faced segregation in employment and housing, both at the Hanford construction camp and in the surrounding towns. The rapid population growth revealed issues not only in housing, but civil rights and policing. In fact, Jim Crow-style segregation really began here in the Pacific Northwest when black migrants moved here for war work. They recruited about 120,000 people but only 45,000 were here at any one time, because this was a very remote place. It was very harsh conditions. Because of all the construction and the winds, there would be massive dust storms that would they'd turn the sky black. They would sometimes they'd make it hard to breathe. The dust would flow into buildings. It would pile up in windowsills, and we were far away from a lot of other towns. So while the wages were good and the work was important, for some people, this was not a place they wanted to be during the war. But why don't we go back to the B reactor to learn more about the making of plutonium?
All right, let's go. Why is it called the B reactor?
Oh, that's a really good question. So DuPont laid out a number of areas and named them for letters of the alphabet, going A through F. So this is taking what Fermi had done in the University of Chicago, but expanding it in a big way, as you can see. So here's the front face, 2004 tubes, process tubes in this graphite block. They didn't even know what they were doing in this entire time. Like, they had no idea that they were building a nuclear reactor. They wouldn't have even known the words nuclear reactor.
Earlier, you were talking about how plutonium needs to be enriched to be a proper fuel for a bomb. Why is that?
So plutonium is a very heavy and unstable element, and so it generates heat. And so that's why it's great fuel for a bomb. This reactor behind us helps take uranium, an element that's a naturally occurring element, and turn it into plutonium, which really doesn't occur in nature. It's a man-made element.
How does the reactor work?
Let's head to the control room and find out. So we'll come around the corner and I mean, look at all of this, what looks to us like really old technology, chart paper, pressure tubes, dials, switches. You notice there's nothing digital here. So this entire reactor was operated in what we call like analog, right? They were reading things on paper and on pressure dials and things like that. Isn't that amazing? Like, this new technology was totally reliant on all these old, and most of these systems actually they got from the Navy.
That's cool.
All right, Sarah, so now we're here in the control room, and this is really kind of like the heart of the human activity in the reactor. And in this room, they're going to monitor different things like the pressure behind us and then the temperature gauges, which we'd be looking at. And that's going to tell us what level the reactor is operating at. And the physicist on staff is going to be taking the temperature of each one of these tubes where the fuel are in, and that's going to let them know when they're at the right level that they want to discharge the fuel so they can get the plutonium out. And one of my favorite things in the control room is they would type in the pressures. So here's the front face. Here's the hottest part of the front face. And this is like the outside, not quite as hot. My favorite thing is that this is secret after fill-in, because what they would fill in here is the temperature. So this sheet of paper is nothing, but the temperature the reactor operates tells you how much plutonium you're making and how much plutonium, or in the 40s, what they would call product, is very secret.
This seems dangerous and careful at the same time. How did it affect the people and wildlife?
People would wear certain types of clothing. We call them like whites, overalls, coveralls. If they went into an area where there was above average radioactivity present, they would dress up. They would don clothes to protect them. They would wear dosimeters, either badges or pencils that would measure radiation in the air. We had never really produced plutonium at this kind of level before. So we weren't super knowledgeable about how this radioactivity would travel in the environment and how it would affect the environment. But the main goal was to make plutonium, and so during the war there were some emissions, higher than would be allowed after the war.
Wow, thank you so much. I learned a ton today. Thank you, Robert.
Oh, you're welcome.
The fuel for the atomic bomb was generated here and in Tennessee. The quest for these products changed the landscape greatly for the people of the past and the present.
Now that we've gotten to take a look at the B Reactor, we're going to move on to our hands-on activities for the day, well, interactive activities for the day. Again, if at any point during this webinar you have any questions, you can enter in your questions into the comment bar and we will be able to answer. So first, we're going to do some math. So I just want to preface this by saying that I think this is super exciting and super fascinating. The great thing about this is I feel like the math in this, doing some of these simple math equations, is really going to help us to understand what exactly is happening in nuclear fission and how plutonium is made from uranium. It's just going to be some simple addition and subtraction. And once we kind of go through this, I think it's going to be a lot more clear what's going on. So we're going to take a look first at what is happening when uranium-235 undergoes fission. So we start with a neutron over here, a little lone neutron, and it's going to impact with the uranium-235. So what happens is briefly the uranium, excuse me, 235 is going to absorb that neutron and briefly become uranium-236. That's going to be too big for nature to really handle, so it's going to break into two pieces. So it's going to break into krypton-92 and barium-141. So there are different combinations of elements that uranium can break into, but in this exercise, we're just going to look at krypton and barium. So we're going to be looking at how all these numbers add up. So if we're looking kind of at two sides of an equation, all the neutrons on this side are going to have to equal all the neutrons on this side. All the protons on this side are going to have to equal all the protons on that side. So we're going to be using the equation that we used yesterday. The atomic mass is going to equal our protons plus our neutrons, right? So if we're looking over here at krypton-92, 92 is going to be the mass of that element. And if we know that it has 36 protons and we want to figure out how many neutrons it has, we're going to use that. We're going to use this equation over here to figure out how to find that. So what we're going to do is we're going to take 92, we're going to subtract 36, and that's going to give us the number of neutrons that we have. So what is 92 minus 36? All right, so we got 56. We got 56 neutrons. Then we're going to come down to barium. So if we know that barium-141 has 85 neutrons, and we want to know how many protons it has, again, we're just going to use that simple equation. We're going to do 141 minus 85. So 141 minus 85, what is that? So again, it is 56. Okay, so we talked about how everything over here has to equal everything on the other side. So if we want to add up on this side of the equation, we know we have 92 protons, but we're going to add this one neutron to our other neutrons that are in uranium. So we know on that side of the equation we have 144 neutrons. So if we're looking at krypton and that has 56 neutrons, barium has 85 neutrons, adding that together, how many neutrons do we have? So we have within these two elements 141 neutrons. So where are the missing neutrons? What happens? So that's where these other three sort of floating neutrons are coming into play. So uranium, when it undergoes fission, is going to burst out krypton, barium, and then 3 additional neutrons. So in that 3, we're taking into account the initial neutron that sets it all off. So uranium, if you subtract that original neutron, gives off on average about 2 additional neutrons. It's about 2.5. So we have 2 additional neutrons that are being shot out. Then these 2 additional neutrons are going to go and interact with 2 more uranium neutrons, and it's going to cause a chain reaction. All right, so let's take a look at plutonium. So plutonium, when we start out, we have plutonium-239, we have 94 protons. So how many neutrons are we going to have in plutonium-239? Again, we're going to go 239 minus 94, and that is going to give us 145. Okay, so that means that on this side of our equation, we are going to have a total of how many neutrons? 146, because we have this original one plus the 145 from plutonium. All right, so let's look at what plutonium turns into. So some possible element combinations are yttrium-96. So if we want to find out how many protons are in yttrium, we go 96 minus 57. Alrighty, so if we're doing that, it's going to be 39. And then cesium, if we want to know the atomic mass of cesium that's being released here, we're going to add our protons and our neutrons together. So 55 plus 85. Anyone can do that quickly, 140. Okay, so if we want to know how many additional neutrons plutonium is putting out, again, we have to make sure that the neutrons on this side are equal to the neutrons on this side. So if we know we started out with 146 neutrons, we're going to add the number of neutrons that yttrium and cesium have together. So 85 plus 57, that is going to give us 142 neutrons. So if our elements are accounting for 142 neutrons, and we know we started with 146, then how many extra neutrons do we have? All right, so yeah, we're gonna have 4 additional neutrons. So again, subtracting that original neutron, plutonium is gonna give out on average 2.9 or 3 neutrons. So what's really interesting about this is if you're looking at uranium fission, it's giving off about 2 on average additional neutrons, while plutonium is giving off 3. So plutonium can actually undergo fission a lot faster. That chain reaction is gonna happen faster. So that has a lot, that's really important for a lot of reasons. So initially in the war, in the Manhattan Project, they were working with uranium, and they came up with a particular style of trigger that would work for uranium. But when they started working with plutonium, they realized that plutonium, the chain reaction would happen too quickly for that original design. So they actually had to change the design. So the bomb that uses uranium is actually going to be a completely different design than the bomb that uses plutonium. It's also interesting to know that because plutonium undergoes the chemical or the chain reaction faster, you actually need a smaller amount of it, so you don't need as much of it. So the critical mass of plutonium is going to be smaller than that of uranium. Okay, cool. All right, so now we're going to take a look at what happens in the B reactor. So how does plutonium get made from uranium? When we start with uranium, we just have uranium-238 and we add a neutron. So why does adding 1 neutron end up with a new element? New elements, remember from yesterday, we have to add protons. So where are the protons coming from? And how are we keeping the same mass? It's really, really interesting. So we start with 1 neutron. It comes into contact with uranium-238. So uranium-238 is going to intake that neutron, and it's going to turn into uranium-239. Okay, so we got 92 protons. We've added here. We've added 1 neutron, so 147 now. So uranium is already really big to begin with. So when we add a neutron to it, nature doesn't really like that. The nucleus then becomes too big, so it has to discard something. So the nucleus is going to undergo something called beta decay. Super fascinating process. So what happens is one of the neutrons is actually going to get converted. It's going to get changed into a proton and an electron and an antineutrino, but we don't need to worry about that right now. So we're just going to look at the proton and the electron. So we take 1 neutron and it turns into a proton and an electron. The nucleus is going to eject the electrons. So that's this little guy up here. He's getting rid of the electron, and he's going to take in, he's going to keep that proton. So then if we come down here, we see that we have now added, right? We've added 1 proton and we've taken away a neutron. Okay, so we've taken away a neutron because it's become converted and it's been changed into a proton. So we take away a neutron, add a proton. Now this whole process happens in about 23 and a half minutes, okay? So the first round of beta decay happens in about 23 and a half minutes. It turns uranium because we're adding a proton. Remember, when we add a proton, it changes the element. So now we have neptunium. So what do you guys think our atomic mass of neptunium is going to be? If we start with uranium-239 and we're taking away a neutron and we're adding a proton, is our atomic mass going to go up or down or stay the same? So it's actually going to stay the same since it's evening out, right? We're adding a proton, taking away a neutron. Okay, so it's going to be 239. So we have neptunium-239. So nature still isn't really happy, so it's actually going to undergo a second round of beta decay. Again, it's going to take a neutron, it's going to convert it into a proton and an electron, it's going to kick the electron out, and it's going to keep the proton. So that second process happens over about 2.35 days, okay? And then that's going to give us our final product here, plutonium-239. So given what you know now about beta decay, how many protons do you think plutonium is going to have, and how many neutrons do you think it's going to have? Okay, so remember, we're adding a proton, right? So we started out with 93. That means now we're going to have 94. And we're taking away a neutron, right? And we started out with 146, so that means now we're going to have 145. And there you have it. That's plutonium. So if you guys are ever confused about how nuclear fission or how to get plutonium from uranium, you can impress all your friends, show them this worksheet, do the math. Very exciting. Okay, all right, so we're done with the math for now. So now what we're gonna do is we're gonna move on to another activity. We're gonna make paper cranes. So you can do this at home. We're gonna show a video. It's gonna be much faster than you can probably follow along with, so don't worry about that. We're actually gonna post the link to the normal speed video so you guys can watch it later. You can pause it, you can rewind as you need to, go at your own pace. I just wanted to give a little bit of context and background to the paper crane. So in Japan, according to Japanese legend, cranes are considered sort of a mystical or holy creature that are thought to live up to 1,000 years. So as the legend goes, if a person folds up to 1,000, if a person folds 1,000 paper cranes, then they're granted a wish or good luck. So on August 6th, 1945, the US dropped a bomb on Hiroshima. And on that day, a young girl who was 2 years old, her name is Sadako, she was exposed to the radiation from the bomb. And by the time she was 12 years old, she was diagnosed with leukemia due to the effects of the radiation. So inspired by the legend of the 1,000 paper cranes, she set about folding as many paper cranes as she could. Her family reports that she folded up to 1,400 paper cranes in the hopes that she would be granted that wish of recovery from the illness. She ended up passing away, but her classmates took it upon themselves to make sure that she was always remembered and that her memory was honored. So they started a fundraiser to create the Children's Peace Monument, which is located at the Hiroshima Peace Memorial Park in Japan. And every year on August 6th, it is celebrated as the annual Peace Day. So we're gonna watch the video. So you're gonna need one piece of square paper. If you have origami paper, great. If not, any square piece of paper is fine. If you take a piece of paper and you fold it diagonally and then you cut off that extra part, that's gonna give you a perfectly square piece of paper that you can use. All right, let's check out the video. Okay, so you're gonna start with your piece of paper and you're gonna fold it diagonally in both directions. Flip it over, fold it in half again. So you should have an X and a plus on top of itself. That will make creases so you can fold it into a square. You're gonna fold one side in and another side in to make kind of like a kite shape. Fold the top triangle down. Open that all up so you can lay it down flat in a diamond. Then you're gonna flip it over and do the exact same thing on the other side. Open it up, lay it down flat. Then you're going to make what's called the narrow kite fold, folding in both of those edges, flip it over, do it on the other side. Then you're going to fold over the right flap like a book, turn it over and fold over the right flap again. Now you're going to have two little ears on the top. You're going to fold the bottom leg up, flip it over, fold the other bottom leg up. Again, you're going to fold over that flap like a book, then you're going to fold over the other flap like a book, and now you kind of have, you're going to pull out your tail, you're going to pull out your neck of your crane, fold down the wings, and then you're going to make the head by folding down the top part of the neck of the crane, and you're going to inflate it by pulling gently at the wings. All right, so that was obviously a really sped up version, but you can go and watch the normal speed and fold your own paper cranes. Share your images with us. You can post them in the comments on Facebook, or you can email us. We're going to be posting instructions on that. You can tweet us at WWII Education and use hashtag MPEFT. All right, so now we have some time for some question and answer. So let's see what we have. Okay, so our first question is from Caleb, and he asks, can you visit the Hanford site? Yes, you can. So it is a national park site, but it's not like a lot of maybe the more common national parks that you might know about. You can't just drive in and visit and explore as you want. They actually require that you sign up for a guided tour to go there. So you have to make reservations ahead of time, and they kind of limit the number of people who are allowed on the site. But yeah, you can definitely go visit. You just have to make arrangements. Let's see. So why are uranium and plutonium used and not other elements? Okay, so that's a good question. So uranium by itself, so they're both really, really big and unstable atoms. So uranium already is almost too big for nature to handle, so it's naturally giving off neutrons anyway. It's already naturally radioactive. And so that makes it really great for what we call induced fission. It's really unstable, so it's likely to undergo fission naturally. So that is what makes it really useful. And then plutonium is the same thing. So once we make plutonium, that's also a really unstable element that undergoes fission really easily. So, alrighty. Yeah, I think that's all the questions we have right now. If there's any more that you guys think of, post them and we'll try and answer them the best we can later. Thanks again so much for joining us today, and we hope you guys have a great weekend. Bye.